Alright, so let's continue from the fatty acids. Now, for the fatty acids, we are saying they are just long chain carboxylic acid with carbon length that ranges from 4 to 36 carbons at most. And if it is having 4 carbons, we call it the butyric acid. And the long chain carboxylic acids or the long chain fatty acids that contains about 36 carbons. Most of these fatty acids are found in the brain tissues and also the neurons of the myelin sheath of nerve cells. Now, those that are common in nature, they exist in even numbers, and these even numbers usually it ranges from 12 to 24. The most prevalent in nature is the 16 and 18 carbon. These are the most common fatty acids that you find in nature. Is the 16 and 18 carbon fatty acid. This means they contain 16 and 18 carbon in their chain. They are either saturated. If something is saturated, all the double bonds have been replaced by hydrogens, so they cannot undergo further reaction. Or they are unsaturated. They are unsaturated means they either have one or more carbon-carbon double bonds. Now, they are rarely found in nature. It's very difficult for you to see a fatty acid in its free form unless you see it being bonded to especially glycerol. So fats that we all hear, fats are esters of glycerol. They are esters of glycerol in a way that since they don't exist in their free form, they react with glycerol. Another name for glycerol is the proper 1,2,3-triol. Now this is glycerol and this is fatty acid. So 3 of this fatty acid will be reacting. We are having an alcohol and we are having a carboxylic group. What type of reaction are we having here? Esterification reaction, where you have your carboxylic and your alcohol, the OH from the alcohol reacting. It's also a condensation synthesis reaction because a water will be formed at the end of the reaction. So this is a simple triglyceride or a simple fat. Since you cannot see fatty acid in its free form, this is carboxylate. It is carboxylate because it is deprotonated. The oxygen here is supposed to bear a negative charge. For that matter, this is called carboxylate. If this fatty acid, if this carboxylate end is bonded to a hydrogen, for instance, if it is protonated, they will call this one a carboxylic acid. Now let's try and talk about some short chain fatty acids. Short chain fatty acids in a way that it depends on the number of carbons that is present. Acetic acid, for instance, this is the carboxylate end or the carboxylic end. It's having 2 carbons, 1 and 2. Looking at propanoic acid, it's having 3 carbons with the same head or the same carboxylic head. Butyric acid also with 4 carbons, valeric acid 5 carbons, and caproic acid with 6 carbons. Now let's move on to the medium fatty acids. The medium fatty acids, it ranges from 8. Now what you are seeing here as C8:0, caprylic acid. The colon 0 here is trying to tell you that there is no double bond. Now we are having C10, which is capric acid. Now as you can all see, this is capric acid, but we can see that there is a bend here. This bend here is not due to presence of a double bond. You can see that this one is C10:0. There is no double bond here, but yet it has bent. Why? These are sigma bonds and they have the ability to rotate freely. For that matter, if the chain continues to be lengthier, it has the ability to rotate and bend. And this also affects its melting point and boiling point as well. The same thing also affects its fluidity. Looking at carbon 12 2, looking at a fatty acid that contains 12 carbons, which is the lauric acid, it has also bent at some point. Now let's talk about the long chain fatty acids. Saturated fatty acids, like I said earlier, they contain no double bond and this contains 40 carbons, colon 0. 16 carbons, colon 0, which is the palmitic acid. 18 carbons, which is the stearic acid. Now let's look at the mono unsaturated fatty acid. Mono means one. So if there is any unsaturated fatty acid that contains only one double bond, then we classify it as mono unsaturated fatty acid. The same thing applies to this one. Contains, now looking at this molecule or this fatty acid, it contains 16 carbons and they've written 16 colon 1. 16 colon 1 means 16 carbons with one double bond, and the N-7 means the double bond is on the 7th carbon when you are counting from 1, 2, 3, 4, 5, 6, 7. When you are counting from the methyl end, this is the carboxylate end, this is a methyl end. The same thing applies here. Applying the same ideology, you are going to see that this one, the double bond is on the 9th carbon, counting from the methyl end. Same thing applies to this one. So this one is the oleic acid and this one is the eicosanoic acid. Looking at the polyunsaturated fatty acids, poly means it contains more than one. So we are having 3 double bonds, and these 3 double bonds, we are having C18 colon 3. This C18 colon 3 is trying to show you that it's having 3 double bonds and it contains 18 number of carbons. And as you can see, they've only represented one double bond. This means that when you are counting from the methyl end, the first double bond that you come across, that should be your position of your double bond. So N-3. Same thing applies here. We are having C20 colon 5. Colon 5 means 5 double bonds. The N3 there is trying to say that the first double bond that you are going to see counting from the methyl group is on the 3rd position. The same thing applies to this, which is the 22 carbon colon 6. Now let's look at the double bonds and also the configuration. Looking at this molecule, this is oleic acid and this one is also oleic acid. They are all fats. You can see the polar head or you can see the carboxylic head. The carboxylic head is also here. But depending on the configuration of the double bond that is present in the fatty acid, it also affects its physical structure, the same time the chemical properties. Now looking at this one contains trans. Trans means the hydrogens are on opposite side. We are having a hydrogen here and we are having another hydrogen here. Looking at this one, the hydrogens are on the same plane or the same hemisphere. So it causes this whole long chain fatty acid to bend, or there is a kink at this portion of the chain. And if there is a kink, it causes the molecule to change its path. So assuming we are all expecting it to move in a straight chain, because of the double bond and its configuration, which is the cis, it has created a kink, which is now moving this way. Looking at the trans, because the hydrogens are on opposite side, it tends to follow this pattern. Now it looks more of a straight, but it contains a double bond, which makes it unsaturated. If you are having this trans, if you are having about millions of this trans oleic acid, this trans oleic acid can position themselves in a way that they will be compacted to each other and they will be able to fit and form a nice pattern where they'll be compacted. And if they are compacted, what happens? The van der Waals forces increases, and if the van der Waals forces increases, it affects its melting point or boiling point in a way that it increases its properties. Now let's look at the cis. Looking at this structure, about millions of them, they cannot find a regular pattern where they will be compacted to each other. For that matter, we are going to find this particular cis oleic acid. They will not be able to compact to each other, so there will be distance between it. If there's a distance, automatically it will affect its van der Waals forces. And if the van der Waals force is less, it affects its melting point and also its boiling point. For that matter, you see these trans fatty acids to have a lower fluidity in a way that they are very rigid or they are solid. But for the cis, they tend to be liquid because of the higher fluidity created by the kink. of the double bond. Now for fatty acids, for saturated fatty acids, the higher the number of carbons, the higher the melting point. That is a general trend. For unsaturated fatty acid, the more you increase the double bond, the lower the melting point. If you are increasing the double bond, what happens? It creates a kink, a bend, which causes the fatty acid chains not to be compacted to each other. If they are not compacted to each other, like I said earlier, it will affect its van der Waals force. If the van der Waals force is less, it will affect its melting point, or it will affect its boiling point. Now let's talk about the solubility. The solubility increases or decreases based on two conditions. The solubility will decrease with increasing chain length. If you are increasing the chain length, it means you are increasing the number of carbons in the chain. It will affect its solubility, since the hydrocarbon part of it is not polar. It will not be able to dissolve either in a polar solvent. For unsaturated, or unsaturation leads to more flexible membrane. If there is unsaturation, there will be more fluidity, like I said earlier. So all what this statement is trying to say is that if there are plenty double bonds, or plenty carbon-carbon double bonds, it's going to affect its fluidity. It's going to increase the fluidity. Now looking at the cis double bonds, the cis double bond disrupts the membrane structure because it introduces a kink. It introduces a kink in the fatty acid chain, causing the carbon chains to bend. I've already discussed this one with you, so if there's a kink, it will be the presence of the double bond. Now let's look at the nomenclature of fatty acids. There are two main ways of naming fatty acids. One, using the omega system, where the carbons numbering starts from the methyl end, and looking at the delta numbering system, where the carbon numbering starts from the carboxylic end. Now when we are looking at the delta designation, mostly or most commonly used, it is most commonly used, and it also specifies the chain length and number of double bonds separated by a colon. So if you are seeing something like this, the 18 here is just to show you the number of carbons. This column that is separating it from the 2 here is to tell you that it's having two double bonds. And now, brackets open, the delta, the 9 and the 12 is just to show you that the first double bond is on the 9th carbon, the second double bond is on the 12th carbon. So that's all they are trying to tell you. If you are having something like 20 colon 5, the moment you see this 5 here, it means that your subscripts, the number of subscripts that you're writing should be 5, because there are 5 double bonds, and this number is representing the position of the double bonds. Now let's look at the omega numbering. The omega numbering, we are seeing that we start from the methyl end. So if you are having omega 3, this means that the first double bond that we are come across will be on carbon 3, or it will be between carbon 3 and carbon 4. That's where the double bond is. So when you are having alpha linolenic acid, which is fish oil, it is omega 3. And why is omega 3? The first double bond that you are going to come across when you are counting from the methyl end is actually on the 3rd carbon. Let's look at omega 6. Omega 6 is the linoleic acid, which is found in vegetable oils. We are definitely going to find your first double bond between carbon 6 and carbon 7. Now let's look at the essential fatty acids. The essential fatty acids, both fish and vegetable oils have a higher amount of polyunsaturated fatty acid, which is what they prefer. Human can synthesize all, but not 2 of the polyunsaturated fatty acid they need. This means that in the biological system of human beings, our system is able to synthesize almost all the polyunsaturated fatty acids that we need, except some 2 main fatty acids, which is the linolenic acid and also the linoleic acid, which are fatty acids with double bond that are placed beyond position 9. So the main feature or the common feature that exists between the linoleic and the linolenic acid is that they have a double bond on carbon 9 or beyond position 9. That's all what we should know about the common difference or the common feature between the linolenic and the linoleic acid. Now, they are essential fatty acids. What are the essential fatty acids? Our body cannot synthesize it, and we have to obtain it from our diet. And this diet may come from either plant or animal sources. And this animal, like we all know, is a fish. There are these two 18 carbons, and another common feature among these two is also that they are all having 18 number of carbons. They are all having 18 carbons in their fatty chains, and they are precursors. If we are saying something is precursors, it serves as an intermediate for something to be produced. So they are precursors for the synthesis of arachidonic acid, which is a precursor. So this arachidonic acid is also a precursor. It also provides an avenue for the synthesis of hormone-like substances. Example, the eicosanoids, which I'll be discussing further with you. Now let's talk about the essential fatty acids. Looking at omega-3 fatty acids are PUFA, which is the polyunsaturated fatty acids, in which the last double bond of the third carbon atoms away from the methyl end of the fatty acids. So they are mostly found in fish oils and the leaves of green leafy vegetables. So the omega-3 that we are all saying, it's the common location where you can see this type of fatty acids is one, either in fish oils, or two, the vegetable leaves, the leaves of green leafy vegetables. You will be able to see omega-3 also there. Now the common omega-3 fatty acids are the linolenic acid and these two acids, which is the EPA and the DHA. This is the linolenic acid. This is the EPA. So as you can see, 18:3. This means that 18:3 is having 3 double bonds, and these 3 double bonds, the position is 9, 12, and 15. So there is one thing that I want you all to know, that most of the double bonds occur subsequently in an interval. If you study this very well, they occur in a specific interval where you find a double bond on the third carbon. The next double bond to find will be on the if you find a double bond to be on the ninth carbon, the next double bond that you'll be finding will be on, let's say, 12. The following will be 15, 18, like that. So subsequently they have 3 carbon intervals for the position of the double bond usually. The same thing applies to the EPA, which is having the 20:5. 20:5 means it's having 5 double bonds. Same thing applies to the DHA, 22.6. 22 means 22 carbons. 6 means it's having 6 double bonds in the chain. And we're having 4, 7, 10, 13, 16, 19. Like I said earlier, they are having an interval of 3. Let's look at the fatty acids, which are essential. Omega-3 fatty acids, they appear to have a lower platelet aggregate, hence the tendency of blood to clot. This omega-3, when you are talking about platelets, is just another type of blood cells which enable an individual to clot his or her blood after an injury. For instance, when someone should get hit right now, within no time the blood will stop because the blood will clot, and these platelets are the ones that functions as the blood clotting. So the omega-3 actually helps in aggregating or aggregation, which also in turn helps in blood clotting. It stops someone from bleeding. So high level of these fatty acids may cause bleeding. If you are having a higher level of these omega-3 fatty acids, it's very likely that you'll be bleeding more. The omega-6 fatty acids, and these are PUFA, in which the last double bond is located on the 6th or on the 6th carbon from the methyl end. Omega-6, like I said earlier, I'll be discussing earlier with you how the omega-6 and omega-3 is obtained. I've already said it earlier that if you have an omega-3, it means that the double bond is between 3 and 4. If you have an omega-6, the double bond is between 6 and 7. So they are mostly found in seeds, most of the plant seeds, except coconuts, cocoa and palm. You can't see omega-6 in the seeds of coconuts, cocoa and palm. The two common omega-6 fatty acids are the linolenic and the arachidonic. So let me go back and this one is the linolenic, EPA and DHA, which are omega-3, examples of omega-3, and the omega-6 we are having the linolenic and also the arachidonic, also an example of omega-6. The reason why we are having linolenic here and also linolenic there is that we still have a double bond on the seed carbon. Now, omega-6 and omega-3 fatty acids are essential fatty acids. High omega-6 or high omega-3 acid ratio promotes the pathogenicity of cancer, cardiovascular diseases, hypertension, arthritis, and all what they are trying to tell you is if you are having a higher ratio of omega-6 to omega-3 or omega-6 and omega-3, then there is a very higher risk of you getting cancer or you'll be prone to cardiovascular diseases, hypertension or arthritis or even diabetes. Mammalian cells cannot convert omega-6 to omega-3 fatty acid because they lack the converting enzyme. If something should occur, if we expect something to occur in a biological system, but we don't have the enzyme for it to occur, this means that that thing cannot partake in the biological system because there is no enzyme, there is no precursor for the reaction to occur. The same thing applies to omega-9 fatty acids. These are fatty acids in which the double bond is located on the 9th carbon, counting from the methyl end. Oleic acid is an omega-9 acid chain. Oleic acid is an omega-9 fatty acid chain. Why? Because it's having a double bond on the 9th carbon, or it's having a double bond between carbon 9 and carbon 10. Now, in summary, all what I'm trying to say is here. Looking at the common name, 16 carbon, 16 is to O or 16 is to 0. It means it has no double bond. For that matter, it's not be having any alternative nomenclature because you're not having any double bond here. If you're having a double bond, that's when you'll be indicating the omega and all those stars. Looking at the stearic acid, it's also having 18 carbons, no double bond, so automatically it will not be having any alternative nomenclature. Now looking at oleic acid, we are seeing that it is 18 is to 1 delta 9. 18 is to 1 delta 9. The moment you see a number that is 1, 2, 3, 4, which is apart from 0, you should bring a delta, and this delta there should have a subscript. The subscript here will be indicating the position of the double bonds. So because you are having 1, we will have only a single number here as a superscript. So we call this one omega 9 because the first double bond that you come across is on the 9th carbon. Let's talk about the linoleic acid. We are having 18 colon 2. This is that we are having two numbers as a superscript, 9 and 12. It means that, and we call this one omega 6. Omega 6 in a way that the first double bond that you come across will be on carbon 6. So 1, 2, 3, 4, 5, 6. So here I think there is a problem here. Let's look at the alpha linolenic acid. The alpha linolenic acid, we are having 18 is to 3, where we are, so the superscript here is actually showing the double bond. It's showing the position of the double bonds. We are having omega 3 in a way that the first double bond that you come across, counting from the methyl end, will be on carbon 3, or it will be between carbon 3 and 4. Now, the reason why we are having the alpha fatty acids have their double bond at carbon 3. So anything at all that, any fatty acid at all that is having a double bond at carbon 3 is called alpha. So alpha linolenic acid, arachidonic acid, 20:4. This means that we're having 5, 8, 11, and 14. And counting from the middle, and we're having 1, 2, 3, 4, 5, 6. Omega 6. Omega 6 because the first double bond that you come across is on the seed carbon. Looking at the EPE, 20:5, it's having 5 double bonds, and these 5 double bonds are located on the chain. Depending on the position, we are having our superscript. This one's omega 3 because you are going to find your double bond on the third carbon. Now let's talk about the elongation and desaturation of fatty acids. Fatty acids are synthesized in the cytosol. The longest length of fatty acid normally synthesized is 16 carbons, which is usually found in the palmitic. So for you to find a naturally occurring fatty acid with a long chain, the maximum will be 16, which is the palmitic acid. Anything at all that you see beyond 16 will result from the elongation and the desaturation, of which I'll be discussing more with you. The palmitic acid can undergo for a palmitic acid to elongate, or for the chain of the palmitic acid to increase, it has to undergo 2 post-synthetic modification. This means that it occurs at the same time, the elongation and the desaturation of the fatty acids. Elongation is just the addition of carbon units in order to increase the chain, and it usually takes place in the mitochondria or the endoplasmic reticulum, catalyzed by the elongases. The elongases are actually catalysts, or let's say enzymes. Now I'm talking about the desaturation. The desaturation is just the oxidation to produce one or more double bond. Desaturation means if something is saturated, you are turning it into to be unsaturated. If you are making something unsaturated, what are you including? You are including double bonds. So this takes place in the membrane of the smooth endoplasmic reticulum. So now it looks like we are having 2 common places where the elongation and the desaturation occurs. The first one, it occurs in the mitochondria, which is the elongation. The elongation part occurs in the mitochondria. The simple ideology behind it also provides energy. We all know that mitochondria is the powerhouse of a cell, provides energy in the form of ATP to be used. For the desaturation aspect, it occurs in the smooth endoplasmic reticulum. Now, the desaturation is all about making the molecule have a double bond, or oxidizing it in a way. If you are oxidizing something, you are removing hydrogen. Hope you remember redox reaction. The redox, we have a reduction. Reduction is the addition of hydrogen. That's the first definition of it. And the oxidation is the removal of hydrogen. So oxidation to produce one or more double bonds means you are removing hydrogens. If you remove hydrogen from the carbons, you are going to make it unsaturated. And there will be a double bond. Now let's talk about the general pathways. Now, let me zoom in so that you get what I'm trying to. So formation of most important fatty acids via the elongation and the desaturation. Palmitates, or let's say palmitic acid. It is saturated molecule. It has no double bond. Now, if you want it to have a double bond, what do we do? Oxidation through desaturation. The same way we can also elongate it. So if you want our palmitic acid, or if you want our palmitate to have a double bond, it must undergo desaturation, which is the oxidation or removal of hydrogens. So a single desaturation will give you a single double bond, and this double bond appears to be on the 9 carbon. That's why we are having 16:1, bracket open, delta, superscript 9. Superscript 9 is showing you the position of the double bond. Now, when you elongate it, you are going to get a steroid. Elongating it means the number of carbons that will be added through one elongation is 2 carbons. So elongation gives you 18.0. Now, we know that these two things are separated. For that matter, the elongation alone adds 2 carbons to it, but it doesn't make it unsaturated. Now, when you elongate this 18.0 again, you are going to get a longer saturated fatty acid such as 20, depending on the number of carbons you are adding, such as 20, 22, 24. Now, when you desaturate it, you are going to get oleates. And the oleates look exactly as the stearates, just that it is having a double bond on carbon 9, or it's having a single double bond. For that matter, it is unsaturated. Now, looking at the oleates undergoing desaturation again, if something is undergoing desaturation, you are still removing hydrogens. For that matter, it will be bearing a double bond. So now it was having a single double bond, but now it's having a two double bonds. So these two double bonds here, we are having the 9 and 12. It means that the double bonds are on position 9 and 12. We have our linolates. Now our linolates can undergo desaturation to give you alpha linolinates, and this alpha linolinate is just the same 18 carbons, but this we have removed 2 hydrogens from it, making it have another double bond attached to the 2. So you're having 3 double bonds, and this is the position of the double bonds, as you can see here. If it should undergo desaturation, if this linolate should undergo desaturation, you are going to have 3 double bonds. In these 3 double bonds, you see here we are having the gamma. The gamma here we are trying to represent. The gamma that we are trying to represent here, it has its double bond between carbon 6 and carbon 7. So carbon 6 and carbon 7. So the first double bond that you are going to see here will be between carbon 6 and carbon 7, or carbon 6. So if this one should undergo elongation, elongation means addition of carbon, 2 carbon spaces. So addition of these 2 carbons will give you this particular molecule. This particular molecule is still having the 3 double bonds because it only undergoes elongation, not elongation and desaturation at the same time. Now, if you should undergo desaturation at the same time, that's where we get our arachidonate. This arachidonate is also omega 6. I hope you understand this part of it. So the same thing also applies here. In plant cell, this is what happens when you are having, this is delta 9 desaturate. Delta 9 desaturate is more like a catalyst which will desaturate it. If something is desaturating, it is introducing a double bond, and this double bond will be positioned on carbon 9. Look at the name of the catalyst, delta 9 desaturates. Automatically the double bond will be on carbon 9. Delta 12 desaturates, which has also oxidized the fatty acid again. Now it's having 2 double bonds. So now we are having our first double bond on carbon 9 and our second double bond on carbon 12. The same thing applies if we are having delta 15 desaturates. We'll be having our alpha linolenic acid, which is 18 carbons with 3 double bonds. These 3 double bonds, we'll be having one on carbon 9, carbon 12, and carbon 15. So the same thing applies here. Very easy for you to understand. Because of time, I'll leave this part to you. Like I explained earlier, if you know you didn't get it, just move back and listen to what I said earlier. You'll be understanding everything that is occurring here in the mammalian cell. Now let's look at the physical properties of the saturated fatty acids. Looking at the symbol and the systematic name, we are having 10:0. The symbol is 10:0. Decanoic acid. Decanoic acid is having a trivial name, which is the capric acid. This is the melting point. The methyl ester is the boiling point. So we are having a lauric acid. These are all trivial names. These are trivial names. Another way around, you can name it systematically. If you are having the decanoic acid and we are having the dodecanoic acid. Dodecanoic acid means 12 carbons. The tetradecanoic acid, tetra means 4, deca 10, so 10 plus 4, 14. Hexa and deca, 6 plus 10, 16. Octa plus deca. So that's how it follows. So when we reach 20, we are having the eicosanoic acid, which is having a trivial name, which is the arachidic. 22, we are having the dough actually represents 2, and the cosanoic acid means 20. So 2 plus 20 will give you 22. The same thing applies here. So that's how come we have our systematic names. For the trivial names, it will be very interesting if you learn it and you become used to it. Now let's look at the number of carbons. So number of carbons here, we are having 16 number of carbons. There is to 1. Is to 1 means 1 double bond. Delta subscript 9 means this is the position of the double bond. Like I said earlier, this is the systematic name. The systematic name is 6,9. The 9 that we are even seeing here should also tell you that the double bond is on the 9th carbon. So here we are having 9 and 12. The moment you see 9 and 12, we are having 2 double bonds. So it will be di. So if you are naming it, it will be 6, 6, 6 again. The 6, 6 again, they are trying to tell you that the first double bond, which is the 9, is having a 6 configuration. The second double bond will also have a 6 configuration. 9, 12, then octa dionic acid. So that's how you go about the systematic naming. If you are seeing 18 with 3 double bonds, this means that you have to mention the position and also the configuration of the double bonds. We haven't 6. This first 6 represent the 9, second 6 represent the 12, and the third 6 also represent the double bond of the on the carbon 15. This means that all the double bonds are in the 6 configuration. Then the octa and their name also follows, as you can see. So right now, I want you to follow the melting point trend. You can see that as we are having only 1 6, we are having only 1 6 configuration for the double bond. We are having the melting point to be 1 degree Celsius. Let's try and look at another 6 9. So this is 9. All they are trying to say is we are having a double bond. It's also having a configuration, the 6 configuration. The melting point is 30. The part that I want you to check out for is this side. The more the 6 configuration increases, the lower the melting point, as you can see. The lower the melting point. Why? Because I said earlier there is fluidity in the 6 configuration, because the molecules cannot be compacted to each other for the van der Waals forces to be also be strong. Now I'll be talking about the eicosanoids with you very soon, so try and stay tuned and look out for my next video on the eicosanoids, which I'll be posting very soon.